There's a set that pops up frequently, and we need to know about this. This is called the empty set. Now, this is a set. The empty set is the set containing no elements. So if I was to write the set, it would look like this. The curly braces, and what do you put in here? Nothing. It's just an empty set. Now we have a notation for it. We're going to use this letter here, or this symbol here, the empty set. So that's the name for this. It looks like a Greek letter phi or phi, phi, but it's not. It's its own font. So the empty set, here's the name of it. It's just a set that contains no elements in it. Here's an example of where this might come up. What if you had, let's call it the set S, and this is going to be the set of all numbers x such that, okay, x is less than 1 and at the same time x is greater than 2. So what numbers are in here? Well, they have to be less than 1 and at the same time they have to be bigger than 2. Well, there are no numbers that are less than 1 and greater than 2 at the same time. So in this case, S is equal to the empty set. Now I'm going to write a little theorem here that says this. Okay, theorem. Here's a statement that we can prove, and we'll actually prove this. For any set S, so for any set that you can think of, to any possible set, this is true. The empty set is a subset of S. Now I'm going to write a theorem that says this. For any set S, any set at all that you can think of, it can be any set that you want it to be. This is true. For any set S, the empty set is a subset of S. We're going to prove this theorem, and the proof uses this idea of contradiction. So this is a proof by contradiction. Now that means that we're going to assume one thing and show that we get a contradiction, and so that assumption has to be false, and whatever's left has to be true. To get an idea of how this works, think about this problem. I'll pose something to you. Suppose that behind this door, I tell you that behind the door there is a cat or a dog. You don't know which. Right? It's one or the other. It's nothing else. It can be only one of these two things, a cat or a dog. And now, I want you to tell me what it is, the cat or the dog, but I'll give you some additional information. I will tell you it's not the dog. So what do you know? What can you conclude? What's behind the door? It has to be the cat, right? If it's not this one, there's only one thing left. It has to be this one. So in our problem, what we're doing is this. Here's the claim that the empty set is a subset of every set. So why don't we assume the opposite? Assume the empty set is not a subset of the set S. And I will show you that if we make this assumption, we'll get a contradiction. To see how this works, think about these two sets here. Here's a set, 1, 2, 3, 4, 5. And here's a set, 1, 2, 3. Now, this is a true statement, isn't it? That this set here is not a subset of this. And why is that true? How do you know it's true? It's true because I can find at least one element. I can find two elements in this set that are not in here, right? So this set here is not contained in here because I can find elements in here that are not in here. Now, the empty set is going to look like this. If we write our situation, if we write this one, what if I wrote this? Okay, the empty set. Now, if you think it's not a subset of some set, what if I even write this set here? 1, 2, 3. All right? Look what we did up here. I'm saying that this set is not a subset of this set because I can find things in here that are not in here. Now, what about this? Is this true? Can you find things in here that are not in here? No, you can't. You cannot find anything in here that's not in here. So this statement right here is false. So if you make that assumption, you get a contradiction. And if you got a contradiction, that means your assumption does not work, and the only other alternative is this one, that the empty set is a subset of that set 1, 2, 3. Now I know these proofs by contradiction, they seem a little bit fuzzy, but they do work, right? So what I'm doing here is I'm just assuming, I want to show that the empty set is a subset of every set. So I do it by contradiction, like backwards. I assume that it's not, and then I get a contradiction, right? If I assume it's not a subset, then I need to be able to find something in here that's not in here, and I can't do it. I get a contradiction. So this can't be the case, right? It cannot be the case that this is true. This cannot be the case. So what's the only alternative left is this one. That's the proof. So now I'm going to ask you some questions, and I'll answer them later, but think about them first. See what you think. Here's the first one. Now just answer true or false. That's all they're going to be. This is just like a true or false quiz. What about this? What do you think? True or false? Just take a minute and answer it. I'll answer it later. Here's number 2. What do you think about this? The empty set is a subset of this set here, 5, 6, 7, 8. True or false? Here's number 3. What do you think? True or false? The empty set is a subset of the empty set. And what about this one in number 4? True or false? The empty set is an element of the empty set. The empty set is a member of the empty set. True or false? Problem number 5 is not true or false. Can you write what this is? What would you put in here? Remember, this is the complement. It means what's outside of this set. What is outside of the universe? And then maybe likewise, here's one. What is outside of the empty set? Here's a true-false. The empty set is an element of 10, 11, 12, 13. True or false? Number 8 says this one, true or false, the empty set is not a subset of this set right here. Empty set is not a subset of this. True or false? Here's number 9. What do you think? True or false? The empty set is an element of this set right here. The empty set is a member of that collection. And here's number 10. We'll end it here. The empty set is equal to this right here. The empty set is equal to this set. True or false? Well, maybe you've thought about those for a while. Now I'll give you the answers to what I think they are. So for the first one, the empty set is equal to the empty set. This one's true. I'll just write a T. That's true, right? What is this? This is a set with nothing in it. What is this? Set with nothing in it. These two are the same. For the second one, this says the empty set is a subset of this set right here. Well, we just proved a few minutes ago that the empty set is a subset of every set, so this is true. That was maybe that kind of baffling proof that we made by contradiction, but the empty set is a subset of every set, particularly it's a subset of this one. And what about number 3? This says the empty set is a subset of the empty set. This is true, right? We just proved that the empty set is a subset of every set, including the empty set. And 4, the empty set is an element of the empty set. Well, that's not true. This is false, and this is false because, think about this. This says this thing here is a member of this. So what if you write this, aren't you writing this, that the empty set is an element of this? Now, do you see this inside there? No, you don't. So that means that this is false. The empty set is not contained, is not a member of this. This thing has nothing in it, so you can't have this thing in here. And what about 5? In 5, we want to know what is outside of the universe. Well, what's outside of the universe? Nothing. So we're dealing with sets now, so you don't just write nothing. The answer to this one would be the empty set. What is opposite? What set is opposite, maybe, or outside the universe? The empty set. And then number 6, what's outside the empty set? Well, everything's outside the empty set. And everything, that's the universe, the universal set. Now, number 7, this one says that the empty set is an element of this set right here. What do you think? I'm thinking it's false. because the empty set is a member of this. I don't see it over here, right? If it's a member, you got to see it in there. I don't. So it's not, this is not an element. So this statement here as it's written is false. And in number 8, this says that the empty set is not a subset of this set. The empty set is not a subset of that set. That's false. We had a theorem, right? We proved that theorem using contradiction that the empty set is a subset of every set. So I know the empty set is a subset of this set. So this statement as it's written is false. And in number 9, this says the empty set is an element, a member of this set here. So when I look in this set, do I see this? Look over here. There it is right there. You know, I can see it. It's right there. I know it's in there. So the answer to this is true. And what do you think about this last one? The empty set is equal to this. Well, what is this set? This is a set with something in it. Right now, if I just draw these, look at it if I just draw them. On the left, I have the empty set. Over here, I have the empty set with what's in it, okay? What's in it? The empty set. All right, so what I've got here is that I've got a set with nothing in it, and over here I've got a set with nothing in it. So the way this is written is that this statement is false because this set here has nothing in it. This set here has a set with nothing in it, but it has something in it. Think of it like this. Okay, think of it like maybe a grocery bag. Here's a shopping bag. It's empty, right? Now here's a bag, and what do you do if you have heavy stuff? You put another empty bag in it. So this bag here, this outer bag, is not empty. It's got something in it. It just happens to be an empty bag.